today, as you guys know, we're going to practice how to create the model on a curved steel bridge. We're going to use a composite section on that. We're going to model the tapered section and also model the abutments along with the piles, and also see how we can model the solid structure interactions and use those for dynamic analysis. All right, so the bridge that I selected for you guys is the curved. You can see here we're going to have 3 girders, and we're going to use the composite section and connecting these guys with the dummy elements. So we're going to go into details in more, while we are doing the modeling. And here is the total length of the, this arch is 200 feet, and the total length of the middle girder going to be 212 feet. And if you would like to create the geometry with the center point and the radius, these are the information here. So you have the curved radius and also the center point. So it's going to be the front view, and you see the abutment depth and also the piles along with the pier and then the pier cap. And also we are going to use the cross frames for these girders. All right, so this is the main information about the bridge. I open the Midas and start modeling from scratch. So we go through the material and the section modeling, then we create the geometry. After that we complete the model by applying the correct boundaries and then modeling the abutments, then applying the corresponding loads like a dead loads and also the moving loads, and we run the analysis and go through the details of the result, and we're going to see how you can use those results for your design purposes. Okay, so let me show you the final model that we're going to come up with. So this is the final model. So as you can see, this is complete, and we're going to start making these from scratch and see how easily you can use Midas for such a bridges. If you have any questions, please feel free to type those in. I can't open the microphones because we have a lot of people here and it's going to be very noisy. So send me your questions. I definitely answer those one by one. All right, so let's start the modeling from scratch. First of all, there are a couple of ways to create such geometry. Let's say I'm talking about the curved geometry. One approach is you can simply, if you have the drawings in AutoCAD or MicroStation, you can simply import them using these functions from DXF file, and you can bring in all the geometry and then just assign the section and material property. Another way is the one that I'm going to show you, everything inside Midas. So for doing that, I'm going to create the nodes and then connect those nodes with the function that we have creating the curve. All right. So for that reason, I go to the node and element tab and I start creating the nodes. Clicking on that, we have the options here. So you can just simply enter the dimension. You can set up the units in the right bottom corner right here. Okay. All right. All right, so I start creating them. Let me put this on the feet for now because the main geometry I'm going to create is based on the feet, and then when you go to create the sections, I'll have the data for the inches. All right, so the first node will be 0, 0. Just click apply. It's going to be in the point of origin. The next point I'm going to create, it's going to be 100 in X and then 30 in the Y direction. 30 in the Y direction and apply. And finally, it's going to be 200 in the X direction and 0 in the Y direction. So technically, I'm creating the one that the plan view that I showed you in the beginning of the presentation. So far, I have 3 nodes which I can draw the curves based on. So the reason I created 3 nodes was that we have one function here called create line element on curve. So if you go there, you see that there are a couple of options for creating the curve geometry. One of the options is arc by 3 points. So that's what I'm going to use for this specific project. But if you have the center point and also the radius or 2 other points, you can simply create it by this option, or there are a variety of other options as well. All right, so I created the first one. So what I'm trying to do is that because we have 3 main girders, first I wanna create the other location of the other girders by moving these up and down. So for doing that, I use the translate and simply select the girders. So here I can just click on that and select them one by one, or I can simply click on this option, which is select all. Okay, and then in the Y direction, I want to go upward 10 feet and apply. In the Y direction, I enter them into X. All right. All right, and then to select them again, here we have only 3 points, but it's good to know there is a function here, select previous. So if you click on that, all the elements or nodes that previously selected would be selected again. So this time we'll go 10 feet downward. All right. If you look at the main geometry here, if I go to the top view, you see that these are not straight with respect to the main, coordinate system. So therefore, I have to rotate these 2 abutment parts. How to do that? I can simply select these elements, these nodes right here, and then go to the rotate nodes. Select the rotation angles, which is going to be 30-degree counterclockwise, and select the first point about the Z, and then select the first point going to be this point, and ensure that it's on the move, because we're going to just move this function, these nodes, and apply, and it's simply rotated. The same thing we're doing for the other side, but this time because it's a clockwise, we're going to enter as a negative 30-degree. And change the first point, which would be right here, ensure it's on the move, and apply. All right, we got this point. And now the next step is to create the main curves. As I just told you, we have this option here, create the line element on a curve. So as of now, I have not defined the material and then the sections. Okay. So if you have not done that, so here simply you can click on this option. For example, under the material, you see there is nothing in this box. To create it, you can simply click on this option, and it's going to bring you to the part that you can define material. Click add, and simply you can just select the steel or concrete, and then go ahead. Now I want to select the steel based on the ASTM standard. I'm going to select A53 and say OK. And for the sections, I can also do the same thing. But that's not a, you don't need to do it right away. What you can do, you can just define the sections later on, and assign them to the elements. For now, it's going to be just line elements will be created. So I'm going to show you how it's going to work. Let's say you forgot this section, or you don't know what section to define right now. Then later on, we're going to define it. All right. So as I said, I'm going to select the arc by 3 points because I have 1, 2, and 3 points for each girder. To make it smaller, I'm going to use the number of segments to the 40 pieces, because the software is going to break them down into 40 pieces. So the smaller elements that we have, the more smooth curve we're going to get. All right. So I select it as a 40, and then click on the P1, select the point 1, point 2, and finally point 3. So you can see how easily the curve is created. The same thing we do for the other parts. All right. And as you can see, these are all in the same alignment. As you can see, these are all in the good direction because we behave them initially similar to each other. All right. If this coordinate system X, Y is in your way and doesn't let you to see the model easily, you can simply turn it off by going to the display and go to the view and uncheck this one and apply. You see it's gone. But I prefer to keep it for now because that's going to help me to understand if I'm going in the X direction or Y direction. So it's a kind of helpful option for now. All right. So far what I have just say 3 curves, which as you can see there is no element is assigned to them. You see them as a line. And if I come back to the main menu, you see that this is showing in the red, which means the section is not defined at all. So to define the sections, what you can do, you can simply go to the properties and then section property and then define them right here. Also, if you click on this option, the red one, it also brings up the same dialog box and then you can simply define them. If I click add, as you guys may know, we have different type of options. We have from the database, like a classical shapes, and also we have you can enter them as a user defined or based on the code. But now what I'm going to define, I want to use a composite section. So I'm going to have my I-shape girder plus the effective width of the slab. So before doing that, I want to just switch this to the inches. So all the units I'm going to use are going to be in inch. Click on that and composite. Just give it a name called steel girder. And here you can select the type of that. I want to select the steel I girder. And here you have 2 parts. One is the slab width. Here you have also slab. This slab width is actually a total width of the bridge. So software uses this part, this option right here, for calculating the lateral stiffness of the entire bridge. While this one, the slab you see here, is actually the effective width of the slab, which works with each girder to work as a composite. So this part will be calculated for the sectional property. This part is calculated for the global lateral stiffness of the girder. The bridge. All right, so let me enter those. And if you don't want to consider the lateral stiffness of the bridge, you can enter them as the same as a slab width and stuff. So this is what I'm doing. Just I'm entering 120, and I enter 1 girder, and I keep this center to center as 0, so I'm not seeing that effect in my analysis. So I just defining this. The effective width gonna be 120 inches, and the thickness gonna be 8 inch. If I have any hunch, I can enter it, but I don't have any in this project. So in this box, I'm defining the steel girder. Following this diagram, so you can simply enter the dimensions. The total H of the web gonna be 72. The B1 will be 18 inches. TF1 will be 2.4. T-web will be 1.8, 18, and 2.4. Okay. So far you see the section is showing up here. So this is the section I'm going to use it. But there is one more step for the composite section, and it's defining the modular ratio and also the density ratio. So to do that, you can either enter them manually. Let's say modulus of elasticity of steel to concrete, let's say, is 7, and then the density is whatever. But if you want to follow the standard and select the codes from standards, the material from standard materials, just click on this option from database. For the concrete material, I'm going to use grade 5000, and for the steel, I'm going to use A53 and say OK. You see that the properties is automatically punched in here. Another option that we're going to use today is changing the offset. By default, based on the shape of the section, software calculates the centroid of the section. So you can see that here showing as a blue dot. So to change that one and then put it upward right in the top of the girder, where the girder is connecting to the slab, what we have to do, we have to use the change offset. So this is a very useful option in Midas, and then this way you don't need to create additional rigid links in the top of the girder to connect it with the slab. So it's very helpful. All right, so I just set it up to the center top, and by doing that, if I display the offset, you see it placed right on top of the section, which is in top of the slab. But to bring it in top of the girder, what I have to do, I have to just select the user for the vertical offset, and then select the from the extreme fiber, go down 8 inch, which this is 8 inch is actually the thickness of the slab. And I say OK. You see that the red dot is right on top of the girder. All right. So I already defined the first section, and you see that while I'm defining that, it automatically applies to the the girder that I have. Okay, it looks good. But to save time here, and also I'm going to show you one technique, is to import the sections from the previously modeled model file. So what I do, I just click on the import, and let me just find the model file. So actually, this bringing the section, it can save your time when you are having so many sections. But if you have one or two, that will be all right. You can just simply create it yourself. All right. So here I have this, and I say open, and you see the list of all the sections that I'm going to use in this modeling. In this model is already listed here. If you don't want to bring some of those, you can simply bring them to the unselected box, but I want them all to come in. And I say, okay, all the sections are coming in. You can just check them one by one, and if you want to change anyone, you can simply do that. The same thing with the material. So far, I defined only steel. Let me just define the concrete as well. So for the concrete, you need to just switch it to concrete, and I select the grade C5000, and that will be my concrete. Another one, if I want to make this as a weightless concrete, because sometimes we need to use a weightless concrete to model some dummy elements, which they definitely participate in the structural behavior of the structure, but we don't want them to add any self-weight into the equation. So for doing that, I can simply, under standard, select none, and you see all these dialog boxes open up. And for the weight density, I just enter 0, and then call it weightless concrete. Okay. Now I have 3 material and all the girders created. All right. So the next part will be, if I go to the top view, the next part will be modeling the diaphragm. So I just turn them off, and the diaphragm will be actually placed at each 5 points. So what I do, I just go to the node and element and create the element. I can select the material. I can select the section from here. So I call it diaphragm. And creating the nodes. Here's the thing. You see here mentioned intersect node and element. If these are by default on, which means anytime that you are creating any element, if that element, new element, is intersecting additional any other node or element, will be divided into smaller pieces, and then we're gonna have more number of elements. But if you turn them off, they're gonna just, each elements which are crossing each other, they're not gonna intersect, and they are not gonna have any effect on each other. But for now, I want to keep them on. So for now, will be from here to here, from here to here. All right, the same thing from the other end. Okay, So we can turn this on and see how it looks like. Okay, so far so good. Now what I need to do, I need to make the cross beams, so cross frames. So for making the cross frames, as you can see here, I have what I have. I have a actually the one single line here. If I turn it off, you see that there's only one single line. But if I want to make it cross frames, it definitely need to go to the Z direction and definitely need to be three-dimensional. So for that reason, I have to make some nodes in the bottom of the girders and then make that connection down here. So what I do, I just go to the top view again, and this time I want to select the girders, the diaphragm locations. So I double click on them, and then these will be highlighted, and I say select only. All right, so I got them here. I can select them all by clicking this option, and I want to create the nodes in the downward for 76.8 inches. I ensure that's on an inch. Go to the nodes, translate. This time I'm going to copy that and go in the Z direction, negative 76.8, and number of time will be 1, and apply. All right, so you see the additional nodes are created down there, and simply I can just create the other diaphragm down here and then create those bracings. Okay, so how to do that? Again, we are going to the create element. So far we are just doing the modeling. So you see that I'm going to use a lot of these functions, especially for the translate and extrude and also the create. So these are the very being used in this model a lot for the part of modeling. Again, selecting the diaphragm, bracing, and this time we're going to create the bracing one by one, and then again ensure that node and element option are checked. So I ensure that while I'm creating these, it's gonna break down into small two elements instead of one. And now to create the those cross frames, so what can I do is that simply select here, and then you see automatically software recognize the center point. Why? Because we have a filter right in the very right bottom corner right here. You see that it mentioned 2. So it means the software automatically considers the points, the center point of each element. If I increase it to 3, for example, you see at 1/3 options is automatically recognized. And then you can also increase it for more convenience. So it just for now, I just set it up to 2, and I just start creating these cross frames. Just know that now what we did, we actually created these additional nodes down here and down here and down here, but these guys are not connected to the top of the girder because we are supposed to make the girder and these cross frames work all together as one system. So to fix that one, to ensure that those guys are connected as they are supposed to, we're going to use the elastic links of the rigid type to make that connection. So that's a very simple step. And anytime if you did any mistake in the modeling, you can simply undo it. It's not a, you can simply modify your model anyhow that you want. All right, so all the diaphragms are created. There is just one left. I'm gonna finish that. All right, seems we are in a good shape. Now let me just activate all elements. Now you see that I have my girders along with the cross frames. But as I said, this node and this node are not directly connected. Look at here, this is just one part of the, one girder. So definitely top and bottom should work together because we assume that plane remain plane. So this is why we have to connect these points. So what I do, I just go back to the previous view that I had because it's easier to work here. And I want to connect these points to each other. Go to the boundary, and then here we have the elastic link. by the way, we have two parts of the rigid links, two types of rigid links. One is the normal rigid links, where you can select the master node and then you can select many slave nodes and then connect them all together. Therefore, they're gonna work as a like a rigid body or like a diaphragm. But I prefer not to use it for this case when I have 2 points because it's gonna be, you have to always consider the the slave nodes and master nodes and then the regulations that they have. But if you have like a let's say 10 or 20 nodes that you want to connect them to a certain point, so at that point is a very useful option to use the rigid links. So for now, I want to use another type of rigid links that we have, which is elastic links, but I can select it as a rigid type. So they work pretty much the same. I mean, they conceptually work exactly the same. And this one is way easier to work with when you have only 2 nodes to connect them, like what we have right here. So for now, I just select them. As you can see, I can just say 2 nodes and connect these guys to each other, ensure that it's on the rigid. And if you're doing the construction stages, which we are not modeling it today, ensure that you're gonna select the correct boundary condition, because construction stages is all about the groups. So at that point, we're gonna have the structural group, boundary groups, and load groups, and then we're gonna activate and deactivate them at different stage of construction. All right, so I got 2 more. And by the way, if you have a straight direction, straight geometry for creating these boundaries or elastic links, you can simply click on the copy, and it's gonna copy the any number of the links instantly for you by clicking only on one of them. So I can just display them. All of them are placed, and I ensure that my model is working pretty fine. So I just right click on it again and say on display. All right, so far let's see what we got. Again, click on the activate all, and now entire the girders and then the cross beams are connected. By the way, this part of the transparent section you see on the girders, that's the actually effective width of the slab that we selected for the girder to work with them as a composite part. Okay, we have 2 abutments and also 1 pier. So the pier gonna locate right in the middle of the bridge. So if I go to the top view, my pier gonna locate right here. So what I do, I can just simply select this part and say activate, and go to this view. And at this point, I can just start creating the the pier cap and also the pier. And then after that, I can go ahead and do the modeling for the abutment. All right. Okay, so now I wanna model these. I assume that there are bearings between the girder and then the pier cap. Therefore, I need to create some additional node in bottom. So what I do, I just select this node and then model the location of the girders, location of the pier cap, and then we're just giving some spacing like a 6 inch to place that bearing. All right, so again, going back to the node and element and then the translate. This time I'm gonna go 6 inch downward and apply. So those guys are created, and simply to, we can model the abutments here. So I technically, for my pier cap, we're gonna be extended in the left and the right, because if I model it right now, it's gonna be just from this girder to that girder, which is not the correct modeling. So I need to just extend this and then create additional nodes. How to do that? I can just go again to the translate, this time copy, and then select them. For the direction, if you don't know the direction, you can simply click 2 nodes, and as you can see, an arrow will be there. And so you can apply the same thing for the other end. And this time we're gonna be -60, and then so these are created. Now what I do, I wanna model the pier cap. Close that, go to the create element, and this time I wanna select the concrete. And for the material, for the section, I have the pier cap at the end and then pier cap at the center. So let's first select the center. Create it from here to there. It's created. Now for these two sides, I'm gonna use the pier cap end. So from here to here, and also from here to here. All right. So as you can see, this is supposed to be a composite, a tapered section, but this is definitely not what we are looking for. But how to fix that? We need to go to the properties, and here tapered group. I'm gonna give it a name, call it left side, or just left, and then select the elements you want, these two guys, and you can simply click add, and you can see this is going linearly adjusted. But if you want to modify them, for example, you can go with the polynomial and then give it number 2, and it goes downward. So it completely depends on the your design. But if you select the J at end and then the 2, modify, so it goes upward. So this completely depends how you design your pier cap and then how you want to model them. All right, so this one is done. Other one will be right, and then unselect all. This time I'm selecting these two guys, and this time again add, and you can see that the girder is completely finished. All right, so now to model the pier, doing exactly the same thing, because the pier starts from the bottom of this pier cap. I need to create additional nodes right in the bottom of that and then connect them with the rigid links. So this is just for more accuracy and in modeling it exactly as it is in the real life. Otherwise, you can come up with some assumptions, say that, okay, I want to start my girder right here and then go ahead and do that. That's also one possibility. Again, going to the node and elements, translate, and this time we're going -72, which is total depth of this pier cap, and apply. So you can see that it's easily done. And quickly, I want to just go to the boundary, elastic link, rigid link, the rigid type, and select 2 nodes from here to here. Just keep in mind that still we need to come back to this part and model these bearings right here. All right? Or yeah, I'm gonna model the bearings at the end after I've completed those abutments, because we have to place these elastic links back there. All right, to model the this pier, the easiest way is to just go to the node and element and use this option extrude. So the extrude is technically you can extrude or create elements, line elements from the nodes. You can create the planar element from line, and you can create the solid from planar. So it's just make it easier for you to go to the higher dimension. Now I have nodes and I want to create the line elements. Just select that, and I want to go with the concrete material and then the pier section. This time I'm gonna go -72. This is each segment's depth or height, and the number of times gonna be 7. And just ensure that it's negative, and going downward is already created. And I can just activate entire the girder. So far I have the girders and the cross frames, and then the pier cap, and then the pier. All right, we just ensure that save your model time by time in case that you may lose your data. Close. And next part will be modeling the abutments and also modeling the those cross frames. See, here's the thing. If I just turn on if I turn this off and then just activate the top girder. So what we see here, you see we are like most part of the girders are left behind, and they are not connected to each other. So technically the girders are working kind of separately. But when we have the concrete on top of the girder, one of the roles of the concrete is to keep them all together working as a one system, not as individual elements. So we have to simulate that. To do that, I can use the cross beams, which are the dummy elements. Dummy, I mean they are weightless, and they are also perpendicular to the direction of the girder. Therefore, they are not participating in the general bending behavior of the bridge. So this is why I'm called them dummy beams. So to do that, I can just go to the create element. This time I select a weightless concrete, and for this for the section I selected dummy cross beams. And simply I just connect them one by one from here. And if I turn this on, you can see that they will be covering entire the surface. So what we do for the dummy cross beams, for the thickness of them, we are selecting exactly the same thickness as the concrete has, and then for the width of them, depends on how did you divided these girders. So for example, from here to here is about 2 feet. So this is why I model them as the total width of this slab. These elements are 2 feet. So if I turn this on, you can see that these are covering entire the surface. Just keep going to finish these. And again, keep in mind to check these nodes and elements, because each time I'm doing that, this is connecting the two exterior girder with the middle girder as well. Otherwise, if those are off, so the first girder and the two exterior girder will be connected, but the middle one will be left behind. All right, so I'm done with this part. Let me turn it on. It seems that I missed one part. Again, going back to the create elements and dummy beam weightless, and quickly create this part as well. All right, that's completed. All right, so again, we can use these functions for we can use these dummy beams for the load distribution, traffic load distribution. So through these elements, the traffic load will be distributed more evenly compared to just using applying the traffic lane right on top of the girders. Okay, so this part is done also. Next part I'm going to start modeling will be the abutments. For creating the abutments, again, I'm going to use the extrude option. This time I'm gonna use the extrude. I want to extrude the beam element and model the plates. So how to do that? I want to use this part. Let me just come here, activate only this part. Then it's gonna give me more room to work. All right, I need these elements right here in the bottom. I wanna copy them 1 feet down. So what I do, I just go to the translate element and then go in negative 12" downward, and this time I want to copy them and say apply. All right, so this is done. This time I'm using these bottom elements just as a tool. I want to just use them to create my abutment, and then later on it automatically will be removed. I'm not going to use this as a structural element. So you see how it works. Again, going to the extrude, and under the extrude select the line to planar elements, and you see here the source. You have option to remove that. So I definitely keep this on, and after the abutment is created, this option will be removed. This beam, sorry. All right, I select this, so I can simply select that, or you can click on this option, which is select the recent entities. Automatically selects the latest elements or node which are just created. For the material, I select the concrete. For the thickness, it seems that I don't have any thicknesses defined here. So thickness is technically the plate elements that you can define in Midas. To do that, I can simply click on that, and again I can import them from my previous model. So I just simply select those, and those guys are coming here. One of them has a thickness of 24 inches, another one is 12 inches. So I just select that, and going downward -2 feet or 24 inches, and the number of time would be 10 times. And ensure that this one is checked off, and say apply. So as you can see, the abutment is about to form. Okay, so this is just one part of the abutment, and as you can see, that those beams that I used, they are already gone, and I'm not gonna use them anymore. All right, so this is one part, and now let's close that. I wanna copy these parts to the sides to create those wing walls as well. So how to do that? I just select these elements and say I want to translate them in the direction which is from here to there, and the number of times will be 2 times, and apply. All right, the same thing I want to do for this side. So this time I can select both of them, and then this number of times will be 1, and the direction will be from here to here, and apply. So I just showed you 2 different methods for creating those. All right, I got this. Now I got to rotate these 2 wing walls. How to do that? We have options for rotating the elements and rotating the nodes. Both of them gonna work for you. I prefer to use the rotating the nodes and then move them, because whenever you rotate the nodes or move the nodes, technically it's gonna carry the whatever elements that is connected to them. So I just use that. Angle of rotation going to be 30 degrees in the counterclockwise, and then about the Z, and I select this point right here, and I need to select my elements as well, or the nodes technically, and apply. All right, as you can see, this is going in the correct direction as I wanted. Same thing for the other side, but this time we definitely should go with the negative 30 degrees, because we are going to counterclockwise, with respect to the global coordinate system. And this time the first point will be this point, and apply. All right, that goes fine so far. Now the abutment is actually coming upward as well to cover this part. So how to take care of that part? I just go to the side and I select all these elements, and I say I want to copy them at top to the top of this abutment. So I use the translate again, this time going 24 inches or 2 feet upward, and then 4 times I want to copy this. Ensure that it's on a copy and apply. All right, it's covered, but I want to use a less thickness for the concrete behind this. How to do that? All right, so I have many elements here. To get rid of those, what you can do, you can just simply double click on the plates. All the plates are activated, and then you can say activate. So now I'm not seeing those elements. And how to change this one? I want to change this with the smaller, thinner elements that I have here. So just simply select these guys. All right, and drag it from here and then drop it here. It automatically converts it. As you can see, I adjusted the point or the offset option, because the same concept that I showed you for the plate, for the girders or beam elements, we have for the plates, where you can just simply apply the plate offset. So you can just adjust the location of the girder, these offsets. All right, let me see what we have. Activate all. All right, so far so good. We see that the girders are here on top of the abutment, and then we have to connect them with the links or the bearings. And now I want to model the piles, and after we model the piles, we're gonna just mirror entire thing to the other side to save the time. All right, let's create the piles. So you can assume that how do I create the piles, because we just did it for the pier. It's very easy. Just select the nodes that you want to apply pile on. So it's going to be these 5 points. And go to the extrude again. Ensure it's node to element, concrete, and the piles. Going downward, negative 48. And this time we're going to model this as a 4 times and apply. Alright, so these are the pile are modeled. Again, you can just play around with them to adjust the eccentricity that they have and those offset options. Plate element, I select them all along with these piles. So now what I'm trying to do, let's say activate these all. I want to assign them to a group. So if I go to the group tab, I can, under the structure group, I can create 2 new groups. One of them would be abutment, and another one would be cross frames. And yeah, those 2 will be the mostly used. And also we can model the girders, because we're going to use for one option that I'm going to explain to you later on. Alright, so I select them all. Abutment, I just drag and drop it here. It's automatically applied to this. Activate all. So this time I double click on this. It selects all of those. And go into the node and element again. And this time we're going to use the mirror option. Click on the mirror. And this time we're going to go in the YZ direction. So I go to the top. I want to reverse the element local, and this time select the 1200 and apply. And you can see that this abutment is applied to the, modeled in the other side. So it kind of saves a lot of our time. All right, there are a couple more small parts to model, and then we go ahead and do the run the analysis. So I try to make it faster to ensure I can cover all the analysis and show you the results, how you can use them for your design as well. Okay. So far we have this. Now the girder, main girders is not connected to the abutment, and also that part. So let's model this connection between the abutments and then the girders. So for doing that, we go to the boundary and then elastic link. Under the elastic link, I can simply define the stiffnesses that I want for them. For the always you see that when we have the lowercase x, y, and z, it means that those are for the local coordinate system. Whenever they are in the capital letters, so definitely they are on the global coordinate system. So now I have the local coordinate system. And then assume that, imagine that we're going to create a one link right here. So dx always is along the direction of the element. So this vertical direction right here will be local x direction for the bearings. So I enter a very large number because I want to be completely rigidly transfers over the load without any, having any elasticity. For the dx and dy, let's say we are entering 100 kips or 10 kip per inch and then 10 kip per inch, and then rotationals, we just keep them free. And I can simply select 2 nodes from here to there, from here to here, here to here. All right. And I go back to the middle part right here also. You remember that we were supposed to create the bearings right in underneath the girders. Let me turn this off so I have more room to work on. So it's going to be one from here to here, here to here, and here to here. And finally, we're going to go to the other end and okay, and then click here, it turns to green, and then you can simply select. Now I have to be just careful because I have so many nodes here, and I don't want to turn anything off now because we are almost at the end of the modeling. Alright, so this part is done. We model the bearings. We have 9 bearings right now. Now a couple more things to do for the abutments. So for the supports, One would be the applying the supports here. I want to define normal support, so go to define support, and then here I have the translational and then the rotational degrees of freedom. Let's say I want to fix them all for this part, so I just select this and apply. It applied. And for the piles, I assume that I want to model the soil springs for those. Okay, so if you have your value, your data for the soil springs, you can simply go to the point spring and enter those, stiffnesses for different degrees of, directions, and then apply them on different nodes. But if you don't have them, we have one wizard here called Integral Bridge. So if you click on that, it can automatically create a linear and nonlinear springs, soil springs, both for the abutment and also for the pile. I want to just go ahead and do it for the pile. For abutment, it's going to be exactly the same thing. You need just to fill up this information. Pile is like quicker. I just do it for you. Here, type of soil, I assume that is sand. Ground level gonna be it's on the inch. Put on the feet. I'm gonna go 28, and the diameter of the feet will be 1 feet, and ground level will be 28, and the pile diameter, and then 150 here. And I select the piles, piled nodes right here, and the other side as well. So what is important is not elements here, it's just the nodes. I want to ensure that all the nodes in the bottom are selected, and say apply. So you see automatically apply the automatically applies the springs on the piles. Exactly the same thing gonna happen for the abutments. So as you can see, we have two parts. One is the linear springs. We can display them or undisplay them, and then we have also the linear, multi-linear parts. So you can display them. You see that is on the X and Y direction, and you can just simply go to the tables as well and see the linear and multi-linear properties for different elements. And if you want to change them, so these are automatically created based on the equations that the standard equations from the codes, but you can just modify them if you want them as well. All right, so for now, I think is enough for the boundaries. Let me just show you how to apply the loads. For the loads, if you go to the load tab, we have different options for modeling the different type of loadings. The first one is the static loading. So I can simply create some static load cases. Click on that. For example, I call it self-weight. And for the type, I select the dead load. So whatever type that you select here, it will be affecting the load combination. So later on, when we're trying to define the load combination, and the software can do it for us automatically, the load coefficient for different loads will be decided based on the type of the loads that you selected. So I select as a dead load, and again I call it superimposed dead load, and again I call it as a dead load, and close. For the self-weight, just click on the self-weight, and for the Z direction, enter -1. If you are in the 2D analysis, which you can simply set up the Midas civil to 2D, you have to enter this -1 in the Y direction. When you are in the 3D, it should be in the Z direction. Add. So the self-weight is applied on the structure. Now we can go ahead and define other type of loading. For example, now let's define those beam loads. But before doing that, let me quickly define these groups to make it easier for me to do the selection. Select the steel girder, double click on them, and then say activate. All right, and ensure everything is there, and I can simply select them all, go to the group, and then under the girder, drag and drop it here, so it's all selected. And for the cross beams, By the way, you can have three menus also. Right click here and then three menu 2. So on one of them you could be on the group, and another one you could work on the work tab. So I can go to the dummy crossbeams and select them all. The reason I'm selecting them all, I want to ensure that all the nodes are also selected with it. All right, that one is also selected. I can close that, come back here, and activate all. This time if I select the girders, I have these, and simply I can apply the, for example, element loads. So this time I select the superimposed dead load, and if you define any groups, it's fine. But for the this type of analysis, moving load, load group doesn't do anything. But if you're doing the construction stage analysis, definitely you have to define correct group loading. All right, in the global Z direction, and I call it -5, 0.5, and select them all and apply. So this is how we can apply some, superimposed dead load with any magnitude that you want. Now I want to go ahead and define the moving load for you and then run the analysis. All right, so I showed you how to apply the static load. You can apply different seismic load, define the construction stage analysis, temperature load, but I want to go ahead and do the moving load at this for this model. I just keep these guys on. Turn this off to see only the line elements. The first step is to select the code. Then it's gonna be selecting the. Let me set it up to the inches, and going to the traffic line lane. I'll call it lane 1, and the eccentricity will be -72. For this girder. So let me first select this one, and then here for the load distribution you have two options, lane element or the crossbeams. For this type of girder I prefer to go with the crossbeams because the load distribution will be more evenly done. So I select the cross frames, and we don't have any skew at the beginning at the end, and because we have curved geometry I prefer to go with the numbers. So I'm going to enter the number of the these girders. So how to select those is very easy. You can simply go with these polygons, select all the elements on curve, and here are the numbers, number 1 to 40. You can simply Control-C for the copying and then Control-V for the pasting, and say add and apply. So the first lane is created, as you can see, and then for the second lane you can just enter the lane number 2, and this time the eccentricity will be positive. Always the negative go to the left side of the guide curve, and then the positive goes to the right side of that. So this time we expect to come downward because the girder is right in the middle. The same elements, and this time say add and apply. All right. So you see I defined two traffic line lanes on top of this girder right here, lane 1 and lane 2. And because I selected those cross frames, cross beams for the load distribution, load will be transferred through those guys. But if you select the lane element right here, all the loads first will be transferred to this girder, and then from that girder will be transferred to the rest of the elements. So that's more logical to go with the cross beams, because that's what the slab does for us. Okay. All right. So far we defined those. I can activate all these. I don't have anything to do with them so far. All right. And now we're gonna define the vehicles. I want to define the vehicle. You have two options: add a standard or add user defined. Today we're gonna just model the standard vehicles. I select the HL93 truck, giving the 33% of load allowance, and apply. And another vehicle I'm going to select is going to be tandem with the same load allowance, close. And now let's set up the moving load cases. So far you see all the lanes and the vehicles that are defined showing in the blue. When any option here shows in the blue, it means that it's not assigned to anything yet. It could happen to the elements, to the properties, to the sections, and also the material as well. All right. How to apply that? We go to the moving load cases and add, I call it case 1, moving load case 1. And here the multiple presence factor, we can just change it to 1 or just keep it as it is. And now add. I want these are 2 vehicles that we define. So the minimum number of the lanes will be 0, maximum number will be 2, and I select 2 lanes, add it here, okay. Again, I select a truck, 1 and 0 and 2, both of the lanes, and okay. And because I set it up to the independent, so software, what happens, software runs the truck on 1 lane and 2 lanes and check the result, and does the same thing for the tandem, and then finally provide me the worst case scenario or envelope result for all those load cases. All right, this one is done also. There is one other function here called lane support negative moment. So what this does, Ashton said whenever you have interior support like this, here we have interior support. So definitely we're going to have negative moments right around the interior support or the pier. So Ashton asked us to place the truck in 2 sides of this interior support with a maximum spacing of 90 feet, and 50 feet, and apply 90% of the load to find out the worst case scenario for the negative bending moment. So instead of doing that, software does it automatically for you. So if you select the lane support negative moments, you have option to select them manually. So how to select them manually? You can just simply go to the group, double click on the cross frames, the girders, select the girders, and then just say apply. It's going to add it automatically here, and it's going to consider them. But you can also select only the elements right around the interior support, or you can just use the auto option. So if you go to the automatic option, you can just select the group that we defined, add it here, and it's done. So you don't need to do anything with that. The same thing for the lane support reaction. So it's exactly the same action. You need just to select those nodes and then apply them. Another thing we have, let's go to the analysis control and then set up the moving load analysis control. Let me close this. And under the analysis control, one part is important is the under the frame, ensure that you select the normal and concurrent forces, because by default software just provides you the normal result, which means for the moving load it's gonna be envelope result, which gives you the maximum bending moment or minimum bending moment that each element experienced during the moving load. It doesn't give you like a millions of output for every single cases. It kind of just give you the envelope. But if you are interested to know what is the concurrent forces, which means whenever we have the maximum bending moment in this element, what are the other components like axial forces and the torsions, so software can provide those to you as well. So we say okay. Okay. And also under the load, under the moving load, we have here concurrent reaction groups. So if you select this and then define the, one of the supports, for example, abutment, and then add it here, calculate the, provide you with the concurrent reactions as well. So these are the 2 important parts which I see engineers are interested to know about the, for the moving load analysis. All right, so we are ready to run the analysis. We can simply hit the run and then waiting for the software to complete the analysis. Just to save time, let me just bring in the model that I already have. Okay, we can take the result of this one as well. Right, it takes like a couple more seconds. this is the model that I showed you earlier. So now the result will be, if you go to the result tab, first of all, you can just see all the tabular, the graphical result right here from all the details here, and also you can get the tabular result right here. Okay, but let's see how it works. For example, for the forces, I go to selecting the beam diagram and select for example, bending moments, and just apply. So you can see the bending moments based on the self-weight is applied like that, and this is the results. If you want to see the legend, so just click on that and apply it. It's going to show you the legend. If you want to see the deformed shape, you can also click on that and apply that. And definitely the deformed shapes are exaggerated deformed shapes, so don't judge it based on that deformation that you see here. All right. So let me see if the other one is finished. Yeah, this one analysis is also done, so we can just go ahead and check the result of this. Yeah. All right. So I want to just show you the result of the model that we just created. So going to the result, and then again bending moments. And if you don't want to see the bending moment in the like a diagram, and you want to just see the see them as like an original shape of the beam, you can just click on that, and it's going to show you like a contours, like what you see here. All right. And here, if you want to get the result, so it's good to have the result here, or seeing the graph here. But for you to do the design, probably you need to get the result in the tables. So either you can go through the table result, and then, for example, beam and then forces. That's one option. But the quickest option or the shortcut is click right here on this icon, and it's gonna take you to there. And here you have option to select the nodes, the elements that you want. For example, I enter element 1 to 20, just that simple. Or you can go ahead and select it based on the type. Let's say I want to check the sections. I want to just check the piles or pier and add it. It's going to add only the elements for the pier. The same thing for the other types, or you can select it based on the group. So let's say, to make it like easy, I want to go from the element 10 to 20, just showing you 10 results. Here you can check the forces that you want to see a result based on, and moving load case, maximum and minimum, and then different parts. I want to just select the middle part. That's it. Okay, and it's going to show me the results. By the way, we don't have any load combinations yet. If you want to create load combinations, it's very easy. Here you have the load combination. You can click on that, and let's go to the steel design, and you can either enter the numbers. Let's say I call it load combination 1, and then add different loads that they have. Let's say self-weight with factor 1.6, and then let's say moving load with factor 2, whatever. Okay, so it's gonna add this load case to my results. But if you don't want that, software can generate the result automatically for you. Just click auto generation, and then here, based on the different codes, let's say H12RFD, you can define these functions, and it's gonna create it for you. So for example, here it generates strength limited states and also serviceability limited states. So you see different factors applied to the different load cases. And here's the thing, you remember when we were creating the load cases, I said that based on the type that you select there, different coefficients will be applied to the result. This is based on the code technically. All right. And okay, let's go back to the tables that I have. Okay, so I have a table of result, but how to behave it? So I have axial force, shear, torsion, moment, and all. But what if I have, let's say, 100 or 200 elements here? I want to find out which one is the maximum bending moment. So I can right click on that, do all the actions in Excel, which I don't recommend at this point because you still can work in Midas Civil. Or you can just go with the sorting dialog. So it's a very convenient approach to sort this dialog and find out the maximums or minimums, or do any changes that you want. For example, I want to find out what is the on which element has the maximum bending moment and wonder which load case. So what I do, go to the moment Y and add it here, and there's an option for the ascending or descending order. By default is on the ascending order, so I say sort to see that the minimum numbers for the MY is right here, and then the maximum values are all the way in the bottom. But if you want to see them in the descending order, sort it. So now I understand that this element, element 10, has the maximum bending moment among the all other elements when it's experiencing the maximum moving load case 1. All right. But here's the thing. Now, under the moving load analysis, you see there is an actual force, shear, and torsion and bending. But these guys, these components are not happening at the same time. These are just the extreme result. They are like a maximum or minimum result. But to see the concurrent forces, just right-click on this table and go to the view by maximum value item. Just click on that. It's going to ask you what values you want. Let's say I want just the actual force and then the bending moments. And under the just moving load case maximum. And say OK. It's going to give you this option. For example, for element 10, I know that when the bending moment, component bending moments here, it's going to give me the different option for the axial, shear, and the torsion. So it's going to sort it based on this way. All right. So you can see the concurrent reactions, or sorry, concurrent forces based on these guys. Again, if you want to export it to Excel, you can simply do that. And here again, you can either select them all like this and then copy and paste it into Excel, or you can just right click on that, export to Excel, and it's going to create a very nice report for you. And if you want to see the concurrent reactions, we didn't define any group for that, but here, if you go here, you see that under the table result, there's a concurrent reactions. So you can click on that, and based on the components that you have, let's say maximum, and here I don't have any group defined, so therefore I don't see any result here. All right. Another important thing is let me just show you the maximum bending moments for the moving load case. Right. This is what I get. For example, this exterior girder right here experiencing the maximum bending moment among the rest of the structure. Now, if I want to know what load case or where is the location of the truck which causing that much of bending moments, I can use the function moving load tracer. Moving load tracer is a unique function. Just select the bending moments and select the element. You can type in the number. For example, this is the element 112, and say apply. It's going to show you the load combination or the location of the truck which causes the maximum bending moment at that location. All right. And if you don't want to see them, you can just go ahead under the applied load, turn off this one, so you don't see the values, and you can see the location of the truck. So technically, there are two trucks simultaneously on this bridge at this location, which causes the maximum bending moment at that element. And I can write this or save this as a static load, and then later on I can just run the static load analysis, which is so faster compared to the moving load. All right, that's one option. And if you want to do it again, you can simply just change the element number from here to another one. But I want to just show you, let's check one other option. For example, for the minimum results, I want to check what will be the result for these elements or the other elements. For example, on this one, software is applying the two trucks and the two sides of this interior support to provide me with the maximum negative bending moment or minimum bending moment in this region. All right. So that's the way we can just extract the result. There's a minimum bending moment, and this is the elements which are experiencing these things. Just please consider that these are the envelope result, which means not these elements are not experiencing these maximum bending moments or shear forces at the same time altogether. All right. And maybe one person engineer wants to design the bearings. So how to get the shear forces in those bearings? So you can simply go to the result, and here we have elastic links because you saw that I modeled that with the elastic link. So elastic link, and then here, let's say not all the elastic links, let's say from 30 to 35, and I want to see them based on the maximum shear force, moving load minimum, and also the self weight, and apply. All right, so you see that it provides me with some forces here. So definitely the axial force, which is in the vertical direction for those bearings, is pretty high because I checked them based on the self weight or the moving loads. But you see the lateral loads also here. These are the lateral direction, Y and Z, and then based on that you can select your bearing type, or you can design it as you want. All right, so that's also another type of output that we can get. So we can simply check the deformation and then the reactions right here, and then it's going to provide you. Just know that because you see here we had these moments, the supports. Just keep in mind that these results under the moving load, because sometimes engineers do some mistake, and they are checking for example, in the vertical direction, they are checking these reactions, and then say the results are not matching with the total self weight that they have. Just consider that these guys under the moving loads are not happening at the same time. Again, I'm just repeating this one. If you want to check the concurrent reactions, you have to just select these nodes as a group, and then go ahead and do the analysis for the concurrent reactions. And yeah, that's all I want to share with you. If you guys have any questions, I keep this session open, and then we can discuss more in detail. We are a little out of time. Okay, I see a couple of questions. Daniel asked if we can use the rolled section for the composite. Yes, definitely we can do that. And we just can't directly import it here. We define them as a, if I go to the property and then defining a section, add, and under the composite, we can just define these options, or like just define them as they are. So we don't have like automatically imported here, but you can just simply enter them right here. Yeah, Andrew said that if we have a flared girders, is there any way to define the composite section? See, we can define those as a, if I go to the tapered section, we have options for defining, changing the width of the slab, but I'm not sure if this is going to be, what you need to do, because under the tapered section, we have all the options, including the composite section. Let's say steel eye girder. So here, for the ith end, we have the slab width. For the jth end, we have slab width as well. But probably this is not satisfying what you are looking for, Andrew. But probably we should define different slab width for different part of the, bridge. That will be the best way, I think. Transfers. Okay, if you have any stiffeners, you can simply just add it as a just element, like what we did here. So these are just the cross frames, but if you have a stiffener, you can add it like one element right here, and then how to fix that part, or how to set it up in the right location. Let me just show you. Let me activate certain parts and apply. Okay. So if I want to have a stiffener here, so I can simply go ahead and define a new section, add, and then select this. Let's say 72, and then a thickness of 1 inch. All right, and I call it stiffener. And okay, change offset, center top. All right, and okay, yes. All right, so now if I create a girder right here, so it definitely gonna show me as a stiffener, for example, from here to here. But here's the thing, because here we have, using a beam element, maybe the that meaning that you want for the stiffener, it may not be working exactly as you want it. But simply I can model it right now. For example, going to the element, create element from here. Let me select this as a stiffeners, and then select it from here to there. And it's gonna, okay, the direction went wrong, but it's gonna be something like some element right here, stiffener. But probably if you model these with the plate element, then the stiffener make more sense because it's gonna work along with the element. But here, what I did to simulate that stiffener, like I just connected the top and bottom of the girder for having that one. But yeah, simply we can just model those stiffeners. That's the short answer. Daniel asked why we entered the minimum number of the traffic lane as 0 and not 1. Yeah, that's a good question. We can just enter as a 1, but the option 0 is available there because when you want to consider for example, you have 5 lanes and you want to just, two trucks run through the entire bridge. So you have option that say when you see the combinations, for example, one of the trucks is not applied on the structure. That's the reason it's already there. Yeah, they asked about the load combination as per H2LRFD. I just showed you how that one is working for the load combinations. So go to the result, and here you can have the auto-generate. And as per H2LRFD, both for the concrete structures, you can separately model those. Okay. They also asked about the difference between the, if I go to the load and then the moving load, see there are difference between the traffic line lane and traffic surface lane. Traffic line lane is used when I have such a model. As you can see, this is a grillage approach. Like I have the longitudinal girders and then transverse girders. So it means I used only the beam element to model the entire bridge, which is a simplified model. So in this way, I have to use the traffic line lane. Traffic surface lane is used when we have the when we are modeling the concrete on top of the girders with the plate element, like what we did for the abutment. If I have a plate element on top, then I have to use the traffic surface lane. So this is the difference between these two guys. They work pretty much the same in terms of like conceptual things, but they have different different time to be used. Whenever you have the girders like this, use the traffic line lane. Whenever you have the plate as your concrete deck, model this as a traffic surface lane. I think we are running out of time, and I answered the rest of the questions with the emails. Please feel free to contact us. We're gonna have all the training materials uploaded on our new website. You're going to have the video tutorials, step-by-step video tutorials, and also the PDF. So please practice this, and anytime you have any questions, feel free to contact us at ts@midasuser.com is our technical support email, and then you can reach us at that point. Thank you so much for your time, and have a good evening.